If two people simultaneously drop identical eggs from a tall building, and one egg is observed to hit the ground before the other, is there any reasonable explanation for this?
No.
What you get?
Assuming there's no wind and they're...
Go ahead.
Oh, that, I mean, if you, eggs have this shape, so if you drop it, so maybe, if you drop the egg one way, and then you turn it around the same egg, another way it could drop a different.
Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
Welcome back. This is Lecture 7, titled Some Basic Physics Problems, or Some Basic Problems. So we're going to use some of the formulas that we derived in the previous lectures to solve some basic physics problems that we might encounter. The first problem is a problem pertaining to average speed, or average velocity. So the formula that we're going to need is that the average speed, or average velocity, is equal to the distance traveled, or the displacement, divided by the time taken. So delta x over delta t. And so what we're going to consider is a problem of, I'm going to try to do some art here. This will be a catcher. And then here we've got a pitcher who has thrown a baseball in a baseball game. So the relevant information that we need to know here is if he throws this ball, and we're also given that it took delta t, the time it took for the ball to go from the pitcher's mound to the catcher was 0.4 seconds. I'm going to write that so that we can see that. And you may know that the distance from the pitcher's mound to the catcher, or home plate rather, is 60 feet. So delta x equals 60 feet. That's this distance here. So we have all the information we need. So all we have to do is plug that into this formula. So the average velocity, or speed, would be equal to 60 feet divided by 0.4 seconds, which is 150 feet per second. Now, that's a fine answer, and it's correct, but we may want it in other units. So we haven't talked a whole lot about units yet, but one thing I will say is that when dealing with physics problems and thinking about physics problems, you should really think in units that you're comfortable with. There are certain advantages to using the metric system, or as physicists would call it, the SI system. It's easier to work with. Converting between, say kilometers and meters is a trivial task, just a matter of adding a few zeros. But if you don't have a feel for that, then you should try and convert to units that you do have a feel for. So 150 feet per second doesn't mean a whole lot to me, and probably not to you either. So let's convert this to miles per hour just to see how that would work. But to do that, we're going to need some conversion ratios. And let me just remind you what a conversion ratio is. So for example, it turns out that there are 5,280 feet in 1 mile. So that means that 5,280 feet is equal to 1 mile. Now if I divide both sides of this by 5,280 feet, then I will get that 1 is equal to 1 mile divided by 5,280 feet. You probably know that multiplying a number or an equation by 1 is perfectly fine. It leaves it completely unchanged. So we don't change anything about the equation or the quantity involved other than maybe the units, which is what this is doing for us here. So if I multiply 150 feet per second times 1 mile per 5,280 feet, which is just 1, right? Then this will give me this rate in miles per second. Now, we don't expect it to be very many miles per second. That would be unusual. Notice the feet will cancel, and we'll be left with miles in the numerator and seconds in the denominator. And so if I punch that into my calculator, let's see what I get here. Let's see, 150 divided by 5280. That's 0.28, we'll call it. No, excuse me, 0.028. 0.028, and that's miles per second. It's not a lot of miles. But of course, that's not miles per hour. We still have to convert the seconds in the denominator into hours. And we can do that through a combination of a couple of conversions. So we know that we're going to want our new units, hours, in the denominator. So we'll start like this. We'll say, all right, well, 1 hour in a ratio will go to minutes, 60 minutes. There's 60 minutes in 1 hour. And I'm going to multiply that times 1 minute in the denominator and 60 seconds in the numerator. And so you can see that that will cancel with that. And I'll get a conversion that will take me from seconds in the denominator to hours in the denominator. And so this is 60 times 60. That's 3,600. And that's seconds per hour. And so I can use that conversion factor in here. So 0.028 miles per second times 3,600 seconds per hour will give me what? Times 3,600. That's 102 miles per hour. So that we have a better sense for, because we know that 102 miles per hour is really quite fast. So that would be a super fast pitch. Not even sure what the world's record for pitches are, but it's probably close to that. Okay, so let's work another problem that's related to this. I'll leave the formula up here for average velocity or speed. And this problem is going to pertain to distance. So I want to imagine that we have a little toy car. That's a terrible looking car. That rolls across the floor at some speed and for some time. So let's say that its speed is 2 meters per second, and that it rolls across the floor. It rolls across the floor for 3 seconds. So the question is, how far does it travel in those 3 seconds? Well, we can find that using this formula for the speed or average velocity by simply solving for the distance traveled or the displacement. So if I multiply both sides of this equation by delta t, I will get delta x all by itself on one side of the equation. And so I can get that delta x is equal to the average velocity times delta t, which is 2 meters per second times 3 seconds. And that will equal 6 meters. So the distance traveled, delta x, is 6 meters. Fairly straightforward, but you will encounter simple problems like that, if not as a standalone problem or exercise, but as part of a problem that you're solving. Let's try another one. This time, let's do one that relates to instantaneous speed or instantaneous velocity. I don't know if you know what a dragster is, but it's these crazy-looking cars that have I think it's basically just a big motor, right? These pipes coming out, it's usually fire coming out of them, and then basically a driver's seat where a driver will sit and drive this thing. And these things are ridiculously fast. And the kind of accelerations that you can get out of these dragsters is, I hear, up to 4 Gs. So what does 4 Gs mean? 4 Gs of acceleration means 4 times the acceleration that we experience on Earth due to gravity. And so you might recall that a G was about 10 meters per second squared. So if our acceleration is equal to 4 times G, that will be 40 meters per second per second. So a lot of acceleration. And we're also going to be given the time of interest. So we're going to say, well, how fast is this dragster going at the t equals 4 second mark? So when t is equal to 4 seconds, how fast is the dragster going? So what's the equation we need to use for this? Well, we need to use the equation that the velocity is equal to the acceleration times the time. And we're going to assume, of course, that this acceleration is a constant during this time interval. Otherwise, this formula would not work. So all we need to do now is plug these numbers into that equation. And so this tells me that the velocity or speed is equal to 40 meters per second squared. I'm writing second squared this time. Times 4 seconds. And that will be equal to 160 meters per second, which is pretty fast, because I know 5-year-old kid is about a meter tall, so that is really fast, 160 meters per second. But let's see what it is in miles per hour. Since we've done that conversion before, we might remember that we need to multiply. Well, actually, we don't have the conversion yet for meters. I didn't give you that. We had feet before. There are 1,609.344 meters is equal to 1 mile. So that's a conversion we're going to have to use. So we'll multiply this times 1 over 1,609. We'll just chop it off there. Meters, and that's miles in the numerator. And so that's going to give us the miles per second. Let's see what that comes up as. So that's 160 divided by 1,609.099. That's 0.099 miles per second. And we remember from last time, to convert the seconds in the denominator into hours in the denominator, we need to multiply this times 3,600 seconds per hour. And so I can punch that into my calculator. Times 3,600. That gives me 358 miles per hour, which is really fast. 358 miles per hour after just 4 seconds. That's some incredible speed. Okay, I think I have one more problem that I wanted to go over. Yeah, and this actually relates back to the last lecture that we saw, because what we talked about in the last lecture would be one way to solve a problem like this. And so this is an apple. So we're going to have a tree again. This is supposed to be an apple tree. And an apple falls a distance of 20 feet. A little tick mark like this is a shorthand for feet, and so I'll use it on accident a lot. And if I do, then just realize that's what it is. Inches would be 2 tick marks like this, but I'm going to just write feet in here now. So it falls 20 feet. Now, we're going to use feet per second squared for the acceleration, the constant acceleration due to Earth. And that turns out G, if you use it in feet per second squared, is 32 feet per second, or per second squared. So we'll put that up there. We'll need to know that. So an apple falls 20 feet from a tree. How long before it hits the ground? Okay, that's the first part of this problem. This is actually a 2-part problem that I wanted to do. And so the first part, how long before it hits the ground, is fairly straightforward to solve. We know that delta x is 20 feet. So let's write down the equation we got in the previous lecture for x as a function of time is equal to x naught plus v naught times t plus 1/2 g t squared. So this is taking t naught to be the moment that we release, the apple starts to fall. I'm going to move x naught over here so that we get x of t minus x naught. But this is just delta x. That's the distance it's fallen. And this will be equal to, we're going to assume the initial velocity is 0. So that is just going to basically go away, that term there. And we're left with 1/2 gt squared. And so what I can do now is solve for t, multiply both sides of this equation by 2 and divide by g. That'll give me 2 delta x divided by g will be equal to t squared, but I want t, not t squared, so I need to take the square root of this, and I'll keep only the positive root. And now we just need to plug in the numbers. So t will be equal to 2 times 20 feet, which is, 20 feet, and divide that by g, which is 32 feet per second squared, so we'll put 32 down here. And I could simplify that up here for you, but I think what we'll do is just punch this into the calculator and see what number it spits out. We get 2 times 20 is 40, of course. Divide that by 32, 1.25, and then we're going to take the square root of that. 1.12, we'll call it. That's 1.12 seconds. So that's how long it took to hit the ground. Now, the second part of the question is related to the last lecture, and that is, if it falls for 1.12 seconds, how fast is the apple just before it hits the ground? Now, you might recall from the last lecture that we actually derived a formula that allowed us to skip this step of calculating the time entirely. And that we could have just simply applied this formula that the velocity squared is equal to the initial velocity squared plus 2g delta x. And that would give us the answer that we're looking for. But since we already have the time, what we're going to use instead is the formula the velocity is equal to initial velocity plus g times t. The initial velocity, of course, is 0, so we just need to plug this in as 32 feet per second squared times the time of 1.12 seconds. And that will give us, yes, this is going to give us a velocity of 36 feet per second. And we could, of course, convert that into miles per hour if we wish to do so. And we've already done that before, so I think we'll skip that here. But I could show you real quickly that we get the same thing if we use this expression here. So again, the initial velocity would be 0, so we just need to calculate the square root of 2 times 32 times 20. And that gives us 36 feet per second as well, which is somewhere around 25 miles per hour. Okay, that's it. The next lecture we'll do a Q&A where we'll sit at a round table and discuss some physics questions that relate to what we've talked about in 1D kinematics. And we'll get some student participation, and so we'll get some idea of the kind of questions that you may have when you watch these videos. Right, thank you very much. Okay, so welcome back. This is a discussion session, or a Q&A, with my two sons and two star pupils, Robert and Gabriel. And so let's just go ahead and begin. We're going to be talking about kinematics in 1D. So describe as many situations as you can where the average velocity is different from the average speed. When would the average velocity be different than the average speed? So what directions can you go? Because
Or backwards.
Forward and backwards.
Okay.
Oh, if we're going backwards, we can't. That would be a negative velocity, I believe, but not a negative speed.
sure, that's right. So if you're going in the negative direction, then your velocity would be negative, whereas your speed would always be positive, of course.
Yep.
Any other situations where you might have a difference in the average velocity than the average speed? Let's take a situation. What if I drive at a constant velocity
I know.
from point, what?
If you drive to one place and then back at let's say 60 miles per hour, the average velocity is different than the average speed.
Yeah, if you make a trip forwards and then back again, right, your average speed will be the sum of the speeds over the two paths, whereas the average velocity in this case would be 0.
Yes.
All right, number 2. Is it possible for the instantaneous velocity to ever be less than the average velocity? Can the instantaneous velocity be less than the average velocity?
What's instantaneous velocity?
That's the average. That's what you'd like, for example, read out on your speedometer. It tells you how fast you're going right now, whereas an average velocity is over some time interval.
I suppose.
Yeah.
Sure, yes.
What about greater than? Is it possible for the instantaneous velocity to be greater than? Let's say my average velocity was 50 meters per second, and my instantaneous velocity, could it be 100 meters per second?
Yes, it can be quick at 1 second and slow down later.
Yes, exactly. So it can be, yes in both cases. Very good. Question number 3. Is it possible for the average velocity to ever be greater than the largest instantaneous velocity? So say we're driving our car in a straight line, and we find that for this long trip that we take, that our average velocity was 60 miles per hour, okay?
All right.
But let's say, I said that wrong. Let's say that over the course of this long trip, at some point along the way, I get up to, say, 75 miles per hour, okay?
Mm-hmm.
All right.
So is it ever possible for the average velocity to be greater than the largest instantaneous velocity? So if the fastest I ever went was, what did I say, 70 miles per hour? 70 miles per hour. Is it possible that my average velocity is 100 miles per hour?
No.
No. It will always be between the minimum and maximum velocities, okay?
Yes, they can be the same or less.
It is an average after all, right?
Yeah, same or less.
All right, number 4. Is it ever possible for a particle with non-zero average speed and 0 average velocity to experience acceleration? That's a kind of a tough, wordy one. You have to think about what it's saying, right? Is it ever possible for a particle, so in this case just some particle, with non-zero average speed, okay, so it's got some distance per time that it's actually traveling, but its average velocity is 0, okay? It could be that case where we took a trip and then returned back to the starting point, so our displacement was 0, right? Is it possible, is it ever possible, for that particle in this circumstance to never experience acceleration? Could you do that without experiencing acceleration?
No.
What do you think, Rob?
Good.
All right, so it does not have a 0 speed. It's a speed cannot
It's a
be.
non-zero speed, that's right.
Yes.
Some positive, well, it's always positive, but some speed. It's not 0.
All right, and it's, what did you say about velocity? Its velocity is 0.
It has a 0 average velocity, which means the total displacement divided by the time interval in question is equal to 0.
And you were asking us whether it can have acceleration.
I'm asking if it, is it possible for in this situation for it never to experience acceleration? So if it never experiences acceleration, that means it's got to be traveling at a constant velocity. If we're traveling at a constant velocity, can we also have a 0 average velocity?
I don't think that's possible.
No, it's not, right? So any loop or circuit will have a non-zero average speed and a 0 average velocity. So in 1D, a round trip, satisfies this.
Because acceleration has to have a change in velocity.
And yes, in this case, it's a change in the direction that's causing the change in velocity. That's the acceleration. Exactly. All right, number 5. If the average velocity is 0 during some time interval, must the instantaneous velocity be 0 at some point during this interval? What about the speed? And you can support your answers with a sketch of position versus time.
Can you repeat that?
If the average velocity is 0 during some time interval, must the instantaneous velocity be 0 at some point during the interval? So the average velocity is 0.
Yes, it must be.
Yes, it must be. So a good example would be if I take a ball and I throw it straight up,
Yeah.
right?
It'll,
And track how long it takes to go, once it leaves my hand until it goes up in the air, it will stop, right? It's under the constant acceleration of gravity. Reverse direction, land in my hand again. The displacement is 0 because it's back where it started, right? But it had that point at the top of its path where it stopped and then reverse direction, so it has to be 0 somewhere.
yeah.
All right, question number 6. If the instantaneous velocity is always constant, can the average velocity during different intervals ever be different? So if the instantaneous velocity is always constant, can the average velocity during different intervals ever be different?
No.
I agree.
Yeah, no, if the instantaneous velocity is uniform, then the position function will be a single line. Since the slope of a line does not vary, the average velocity which is computed from points on this line will always be equal to the instantaneous velocity. All right, number 7. Give an example of motion in which the velocity is negative, but the acceleration is positive.
Example of motion.
And you can support your answer with a sketch of velocity versus time if you want. Example of motion in which velocity is negative, but the acceleration is positive.
Example of motion where the what is negative?
The velocity is negative.
Or the
So I'm
acceleration.
traveling at, 10 meters per second, negative 10 meters per second. But the acceleration is positive.
So
You wouldn't call accelerating backwards negative acceleration, would you?
Well, yes, you would if you're accelerating in the negative. If there's an acceleration in the negative direction. Some people
that
call it deceleration.
But let's just call it
Yeah.
acceleration.
But in this case, we have a positive acceleration. So the acceleration is in what we're defining as the positive direction, but our velocity is in the opposite direction. We're in 1D. So,
Well, I don't see how that can be possible.
well, think about it.
If
If we're
you
traveling in, say, this direction,
Yes?
right? And we call that the negative direction, but the acceleration is in the opposite direction. Now, let me make it easier. Let's say that this is the direction of the acceleration, okay?
All right.
And it's also the direction of the positive direction. So our ruler goes from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right?
Yes?
But our particle is traveling in the opposite direction, so it has a negative velocity. Any ideas what this would correspond to? What would be a good example of this motion? Now, we don't have a lot of choices with one dimension, so if I take a ball
Yes.
and I toss it in the air, okay?
All right.
But I take my ruler and I set it up such that the 0 is up high,
All right.
right? So it's traveling in the negative direction, right?
Yeah.
So it has a negative velocity, right?
Yes.
Which way is the acceleration going? Well, it's down towards the Earth in the positive direction, right?
Yes.
So that would be an example where you'd have that. So what happens to the object? So if we are traveling in the negative direction but experiencing a positive acceleration,
Yes, you're right.
are we speeding up or slowing down?
We are
Speeding.
speeding up.
No.
You say if we have a positive acceleration?
Our acceleration is in the positive direction,
And then
but our velocity is in the negative direction. Are we speeding up or slowing down?
We are.
Throw a ball in the air. Does it speed up as it gets higher, or does it slow down as it gets higher?
It slows
It
down
slows
as it gets higher.
Yeah, it's slowing down.
Then why did you say
slows
falling
down.
or coming
Slows
It's
down?
not falling. It's going up, right?
Yes.
It's traveling in the negative direction.
All right.
At some point, it's going to stop entirely, right? Once it slows down to a 0 velocity, and then it's going to reverse direction. Now it'll have a positive velocity and a positive acceleration, okay?
Okay.
And that, of course, is kind of, well, not really. The next question is, give an example of motion in which the velocity and acceleration are both negative.
The acceleration. So that would be going slower and slower in the negative direction.
Well, the acceleration is negative, and the velocity is negative. So if the acceleration is in the same direction as your velocity, what's going to happen to you?
If you drop a ball
Yeah, if I drop a ball,
down
Yeah.
from like a tree, then tree post, whatever. And the lower down you go, the closer to 0 you go, then would it be having a negative acceleration and negative velocity?
sure, that's right. So if I had my ruler set up, and this is all about which way we align up our rulers, right?
Yes.
Yeah.
Whether we call something a positive or a negative acceleration really depends on which way we lay our rulers out. So if I lay my ruler out such that 0 is down here and 1 or 2 or whatever is up
Whatever's
higher,
up here.
right, then this is the positive direction, and this down would be the negative direction. If
Yes.
I flip the ruler, I flip the sign.
All right.
Yes.
And what never changes, right, is if if the acceleration and the velocity are opposite signs, then that's going to slow down. Whereas if they have the same sign, whether they're both positive or both negative, it will speed up.
All
Okay?
right.
All right, next question. If two people simultaneously drop identical eggs from a tall building, and one egg is observed to hit the ground before the other, is there any reasonable explanation for this?
No.
What about you, Gabe?
They hit it at the same time.
It's the same egg, dropped from exactly the same distance, and released at exactly the same time.
Assuming there's no wind and they're.
Well, if we observe that they did not hit the ground at the same time, then we might suspect there was a little bit of wind that hit one of them along the way. That's one explanation. Any others? Go ahead.
That. Well, I mean, if you, eggs have this shape, so if you drop it, so maybe if you drop the egg one way and then you turn it around the same egg another way, it could drop at different speeds.
I see. So you're saying maybe one of them was falling with a different orientation,
Yes.
and so the air resistance that it experienced was different. That's a possible explanation. But let's assume that they were dropped identically in the same way, so that what faced the air, what the air resistance was the same for both, all the way down. No? Any ideas?
And the ground was at the same point.
Yeah.
All right.
Yeah, that means that's dropped from the same height. I guess.
I don't see how they could hit at a different time. They're the same weight. They're exactly the same.
What about the ruler?
Same position.
Is it
Everything.
the same direction? For
Oh yeah. Oh yeah.
Okay.
Everything about them is the same.
Yeah.
That I don't see it.
Could somebody
I don't-
push?
I don't think
the
that's
person
possible.
who dropped the
Does it
egg
sound possible?
dropped it out.
Yeah, they gave it an initial velocity. Yeah, if you give it a little initial velocity when you drop it, then it's got, some initial velocity plus the velocity that it acquires during the fall, so it's going to get to the ground first.
Exactly.
That's the answer I was looking for. Let's see. Next question. The apex of a model rocket's flight is the highest altitude attained by the rocket. What is the velocity, speed, and acceleration at the apex? So that's the highest point that the rocket goes up.
Zero.
Velocity.
Zero.
What about the acceleration?
Well, the acceleration.
The
It's not
acceleration.
accelerating because it's going to stop and then fall back down.
But is it accelerating? Isn't there still the acceleration due to gravity?
At the
You're right.
highest point.
There is.
Yeah, even though the velocity is 0, there's still that acceleration. okay? Because the acceleration is the change in the velocity during a time interval, okay?
Yes.
And so that on Earth is, you know, about 10 meters per second per second. So, yeah, so the acceleration is still just g, as we call it, little g, but the velocity and speed are 0. Let's see here. For an object traveling at a constant velocity, the slope of the position function, x of t, gives which quantity? Average speed, average velocity, or average acceleration? I can draw a picture if you want me to, but
Yeah.
Yes.
it's just a line, right?
Please, John.
So
Picture.
we have x of t, vertical axis,
Yep.
and t on the horizontal axis. And let's say we've got a nice line like this, okay?
Yep.
So, where'd my question go? Oh, there it is. The slope of the position function, x of t, gives which quantity? So the slope would be the rise over the run. So you could pick a point, say here, and pick another point way down here, right?
Yeah.
So that this distance here, right, and this distance here are the relevant quantities, right? This is the rise, this is the run, right?
Yeah.
Obviously the y-intercept is 0, so we'd have x of t equals m, the slope, times t, I almost wrote x, times t plus the y-intercept, which is 0, right? So what is that slope, rise over run? What are the units on the slope? What is the slope measure? What is the rise measuring? What is the run measuring? What's the ratio of
Rise
those two?
is
X of t. Run is
Well, it's this x position minus this x position. What do we call that? Maybe if I chose a different point to get this slope from, right? What if instead of choosing these, I said, how about we choose these 2 points? So I've got this, and I've got this, right? So the rise, right, would be this x, whoops. We have x of t here. This would be, we'll call it x naught. So this distance here, the rise, is x of t minus x naught. And then here, we'll call this t naught. And we'll call this point here t. So this distance here is t minus t naught.
Yep.
Right?
all right.
This we call delta x, the change in x. This we call delta t, the change in t.
All right.
And the slope is delta x divided by delta t. What's that? Delta x divided by displacement divided by time interval. What is that?
Time. That sounds like. Is that velocity?
It is velocity. It's the average velocity. Okay?
All right.
All right. Next question. True or false? And you have to support your answer with an explanation. The equation x of t equals x naught plus vt, I'll write it on the board. This equation, x equals x naught plus v naught t plus 1/2 a t squared. The question is it true that this equation holds for all motion in 1D? Is it true for all motions in one dimension?
Yes.
You think yes? What do you think?
Wait.
Is it always true?
For
All right. Well, it seems like you guys don't have that one down. The answer is no, this is false. Okay, this is only true for constant acceleration. Okay, and that kind of leads us into the next question. The average velocity over an interval is always equal to the sum of the initial and final velocities divided by 2. Is that true or false? Well, just listen to it. The average velocity over an interval is always equal to the sum of the initial and final velocities divided by 2.
Average velocity. That sounds right. I mean, yes.
Is the average velocity,
Yes.
v sub average, always equal to v naught plus v of t divided by 2? Is that always the average velocity?
It looks like it, yes.
Let me show you a case, okay? Let this be a velocity versus time, okay?
Alright.
Now let's assume we have a constant acceleration. That means that our velocity will be increasing linearly. Okay, so I got another line. Now in that case, if I pick 2 points, here and here, right, and I get these two velocity, we'll call this V2 and V1, right?
Yes.
Which we could then write in like this, right? V2 plus V1 divided by 2. The average of this will be right in the middle, right? Which will be right here. So in the case of constant acceleration, yes, that's true. The average velocity is equal to the actual mean or average of the two velocities taken at 2 different points, okay?
Alright.
Yeah.
But what if it was a curve like this instead? Here's our velocity, here's our time. Let's say it starts out kind of slow velocity and then it speeds up really fast. So I pick a point here, I pick a point here, right? The average of this is going to be here, right?
Yes.
But that is not necessarily the average velocity for this, right?
Yes. Yes, that's true.
Yeah. So this is only true in the case of constant acceleration. Let's see. The displacement delta x is always equal to the product of the average velocity and the time interval. This delta x, let's erase some of this so we have some room to work.
Keep going.
Is delta x always equal to, how did I phrase it? Just make sure I get the product of the average velocity and the time. I guess we call that delta t if you wanted. Is that always true? Okay. No one has any thoughts?
Oh no, I'm pretty sure I have the answer.
What's the answer?
Yes.
Yes, that's the definition of it. The average velocity is defined as the displacement divided by the time taken, right? The time interval.
Yeah.
So this is by definition true. Okay.
It has to be.
Alright.
The previous thing I showed you, right, that the average velocity was equal to the sum of two velocities at 2 different times divided by 2 is not always true. That's only true in the case of constant acceleration. I think that may be the last question. Yes, it is. That was the last question. Okay, I think that went pretty well. I think we fleshed out some of the misunderstandings that we may have had in our understanding of kinematics in one dimension.
Alright.
You feel like you learned something?
Yes.
Good. How about you?
I learned that I'm great.
You learned that you're great. Wonderful. Well, that's an important lesson. All right, thank you for joining us, and that's all we have for this lesson.